הבאה ניפגש במשרד. So, in the previous lectures, we basically defined the eigenvectors of the angular momentum. Used the notation either YLM or just bracket LM. We defined a ladder operator L plus minus and we have shown that up to a constant, and we defined these constants. Okay, now in a similar fashion to what we did in for a harmonic oscillator, we want to figure out what are the eigenvectors and eigenvalues. Okay, to do that, basically let's write down specifically what are the constants. And square root. And basically, just from looking on the definitions here, as we have defined previously, M has to be either smaller or equal to L. If we're trying to add a state above L, we will get here 0, just from the normalization factor, and similarly, if we are trying to move below, we will get 0. Okay, this is a good starting point in order to figure out what are the eigenvectors and eigenvalues of the angular momentum. Okay. So I want to rewrite L plus minus in spherical coordinates in theta and phi. That I'm getting just from the definition of Lx and Ly in spherical coordinates, which we have written down in one of the previous lectures. Okay. So I'm just copying the definition. Oh, sorry, it's a plus minus. Okay, I'm just writing down definitions at this moment. But we actually calculated already the eigenvectors of phi. We wrote it as e to the power I m of phi, but here m is equal to L. So we write L instead of m. And all of this, of course, is equal to 0, according to what is appearing here. Great. So we we can perform the derivative on phi. This guy doesn't have any influence on the part that depends on phi. So we can rewrite what appears here. Okay, I just wrote down the derivative according to phi. Since it's equal to 0, I don't care about all the constants here. And I'm left with an equation let me divide everything by large theta, by the function. Just write down explicitly cotangents. The left-hand side is our good old friend, the derivative of a logarithm. So let's integrate left and right hand side. So the integration on the left hand side is simple, just lambda theta. don't see it immediately, just performs a derivative. So it's 1 over sine. Derivative of sine is cosine. And you have the result. Okay. So constants will be corrected once we write down a normalization. So I'm not worrying about it at the moment. I have some normalization constant times sinus to the power of L. Just because it's a ln, I can take the L and put it as a power of the argument of the logarithm. So just to tidy up, so the normalization will come from squaring it and integrating. Then as the power of sine will come from the Jacobian. Angular coordinates. And now life is good. Why? Because I can go and define can go here and play it actually in several ways. And of course the integral is between 0 and pi. So it's just a power of sine to the 2L plus 1. And because it's between 0 and theta, although it's it's an odd function, nevertheless it's not 0. And we can perform the integral and get just constant of so basically we're finished. Why? Because I can write down LL, and this of course has to be equal to 1, just by normalization. And we get here not simply, just So, what is the strange part in what I have written?
-1?
Right, the -1 wasn't here. Why did I add it? Just to fit with a definition of a polynomial that we'll use in a moment. But since normalization of A is also correct for -A, so I can add this power of -1 to the power of A. Doesn't make any difference for the normalization because we split it. So it's my choice in order to fit it with a known definition in mathematics. Okay. So we solved the problem. Why? Because what did I miss here?
The A.
No, A is exactly this long and ugly.
Okay.
I forgot the phi. The 2 pi went into here of the normalization of phi. Okay, but once I have this guy, I can define all eigenvectors. Why? Because just operate with L-1, whatever, to bring it to whatever value of m that you want. And that's it. So I'll write it down explicitly.
To find the because we just set
I'll write
L or something.
No, I want to find the eigenvalue Ln, right? That was the problem I came originally with, right? So, the algorithm, find LL, written, we did it. Now, you want Ln, operate with L minus, go down the ladder till the value of m that you desire.
Okay.
So, it's exactly the same thing that we did in harmonic oscillator. There we started from 0 and climbed up. Here we're starting with the upper value because we're limited. In a harmonic oscillator, I couldn't start at top because I have no top. I have only the ground state, and there I can climb up. Here I can go down from L, or I could do it the same game for minus L and go up. My choice. So I can write it down explicitly. First of all, nothing happens to the phi component when I'm operating with L plus or L minus, because it's all derivatives of theta, not of phi. So I'm left with the same part of the eigenvalues that depends, eigenvectors that depends on phi. Now I just So this is just going down the ladder. Okay, let's write down explicitly a few terms. Well, actually, this result you could have gotten without doing any calculation, because at the 0, 0 state, I know m phi will give me just a constant. Sine to the power 0 is just a constant, and all I'm left with is with the normalization over an integral, a spherical integral, a constant, which is 4 pi. So normalization will force me to write down 1 over square root of 4 pi.
I still don't get why we can, like, why is it simple? Like, okay,
I'll give you a mathematical answer and I'll give you a physical answer. Okay? Okay. Mathematical answer. We proved, right? But here L is equal 0, so it's sine to the power of 0, so it's a constant.
yes.
We saw that all these manipulations does nothing to the phi component. So e to the power n, which is 0,
It's 1.
it's 1, so everything is 1. So I'm left only with some a 0, 0 times 1. That's the wave function.
Yes.
Okay. So normalization, a 0, 0 squared, let's forget about the 0, 0. From 0 to 2 pi. both are integrals that you can do,
Yeah.
hopefully.
Okay. Then I get
So that's 2 pi, and that's 2.
yes. Okay. Then get that. Okay.
So it's 4 pi. A squared has to be equal 1.
So it's good. Yes.
Now mathematics, but a simpler argument. The solid angle integration, an integration over an angle of a sphere, which is 2 angles, theta and phi,
Yes.
is always gives us 4 pi.
Right.
So I know that that's the normalization, so I can write it down in physical answer, argument. If I have no L and M component, theta and phi have to be completely isotropic. If it's completely isotropic, so the wave function describing it is a constant, defined only by normalization. Go back to what is a normalization, end of story.
So the so still the it's harmonics.
These are the spherical harmonics.
Okay. Yeah. So okay.
And that's why we defined it with a -1 to correspond to the definitions of spherical harmonics.
Okay.
Now, again, it comes out immediately from the definitions. Y sinus theta to the power L equal 1. Here M is either plus minus 1, so it's plus minus I phi, and that's normalization. For M equals 0, there's no phi component, and I have one derivative of a sine that gives me a cosine. Okay, and I can go on and perform this game, or check a table of spherical harmonics. So these are exactly the spherical. Now, if you're studying or you have studied it in mathematics, they will come and tell you, okay, this is a very interesting way to write down any solid angle dependent function, meaning a function that depends on theta and phi, as combination of the spherical harmonic functions. Right, and they are orthogonal, and you can write it down as a series of any function in theta and phi. You can write down as a series of these guys, the spherical harmonic. From the point of view of physics, it's just saying that that's the basis of the eigenvectors of the angular momentum, which depends on theta and phi. Of course, they're orthogonal because they're eigenvectors, and of course you can write down any function because they are a basis that can, using this basis, you can expand any any vector in this space.
Yes.
It's two complementary ways of looking on it. And just for completeness, although we don't really need it at this point, I want to connect these spherical harmonics to the Legendre polynomials, just because it's usually done. Oh, before that, it looks like something special happened here in space, because phi and theta have already a different dependence. Right, I have a difference between L and M equals 0, 1, and minus 1 for M. And that depends on the choice of my axis, right? Theta and phi depend on my choosing of the axis. So, by choosing the axis and asking what is the n component around this axis, I broke here symmetry.
Okay.
Although the potential is symmetric. Just I decided to stick my axis in a particular way that forces me to write down my mathematics accordingly. I didn't break physical symmetry. So if I want to go and move my axis in a spherical potential, for no problem, because the problem at the end of the day is still symmetric. Just I got your anisotropy not because the problem is anisotropic, it's because I chose an axis.
So we can choose one to be symmetric.
Yeah, I can move it. No, I can choose here an axis that will be symmetric.
Or
And this has a very, very, very deep physical consequence. What does it mean? At the end of the day, we know that measurement forces you to be in some eigenvector according to the measurement. So if I choose an axis and choose to measure the angular momentum according to that axis, then I break symmetry. Because if I get m equals 0 or m equal 1 or m equal minus 1, I got a different wave function. But that's because I went in, performed the measurement, and broke symmetry. Because I measured according to a particular axis. Okay, so let's deal with the correspondence between the Legendre polynomials and the spherical harmonics. So as I said, we solved the problem. Now it's just making connections with other mathematical definitions of these functions. So going back to the original differential equation, which is, if we simply didn't use all our tricks of ladder operators, but just wrote down the differential equation, which we wrote down a couple or 3 lectures ago, and we take into account that we know the part that depends on phi. That's why we get here m², just because we have the double derivative on phi, which gives us m² there. So we wrote down the original differential equation or eigenvalue and eigenvector equation for theta ln n. Now, historically, that's how the solution was found. When they solved the hydrogen atom, that's what they did. Now, using the substitution x and we're so a series of substitutions just coming out from replacing cosine theta with x, and sine, of course, is 1 minus cosine squared. So this is the reason for this cumbersome term. Going back to the original equation and substituting anywhere that we have theta or sine theta with these substitutions. And for the case this is a Legendre equation. So, if you are curious why the terms L times L plus 1 were chosen, just to fit with the Legendre equation. Because here, if you remember in the beginning, it was some constant. But the Legendre equation has solutions for this constant only if it's L times L plus 1. So that defines the quantization in L from the mathematical point of view. We found out from the ladder operators that it comes out for a limit on the eigenfunction, so they won't continue to go up and down to infinity. So choose whatever explanation you want. There's a solution to the equation only if L equal L plus 1. There's nothing to stop the eigenvectors from going to minus infinity, which is not allowed, just because you have to have a ground state. So whatever explanation makes you happy, you can use. But that's the reason why we chose L times L plus 1. Okay, we still, Legendre equation actually does, this actually equation for m equals 0 treats the case that is in the middle of our two original solutions. We had LL, we had L minus L, and now we have L0 from the Legendre equation. So, as usual with differential equations, we go and check if some French mathematician in the 18th or 19th century solved it. In this case, Legendre, and we know that its solutions are the Legendre polynomials, which can be written And Legendre, like in all the solutions for this differential equation, wrote down the fact that don't amaze us. One is that they are orthogonal. Of course, they're orthogonal. They are a solution to the composer basis, but and since we got to it from trigonometric function, it's very clear why they are between -1 and 1. There's because this thing really is a sinus. Sinus goes between 0 and 2 pi. Sorry, 0 and pi. And any function in the range between -1 and 1 can be written as a series of Legendre polynomials. Okay, again, it's a basis. What do you want? And it has a generating function which, when you write down as a series with small s, you get the Legendre polynomials, and it has recursion relations. So if you know the first two Legendre polynomials, you can find out all the rest, and that P0 of x is 1, P1 of x is x, so you can go and create the whole list. And what do you do for the case where n is not equal 0? So don't remember if it's Legendre or someone else that wrote down the solutions, but in the cases of where n is not equal 0, so PLN all these forms we have seen before. So that was the roots through differential equations. Don't know how much knowledge it really added for you, but at least now you have the connection with the Legendre polynomials and the spherical harmonics, which at least once in your lifetime it's important to see. Okay, back to physics. That was a mathematical interlude, at least after the first quarter hour where we had the solution in a much, to my taste, neater form. Oh, and the connection with the Legendre polynomial is the reason that we put the -1 to the power of L in the normalization. Just so it will fit with the definitions of Legendre polynomial. Okay, a bit physics. Parity of the angular momentum. You may recall that we did the definition of the parity operator in 1 dimension, but for 3 dimensions, the same type of definition. Or in polar coordinates, spherical coordinates, so R, which is just x squared plus y squared plus z squared, doesn't change sign. The other guys, theta and phi, sorry, I'll be more exact, it's not minus theta. It's definitely not minus. Just flipping the vector according to r, theta, and phi. Because that's exactly what putting minuses gives us. So if I had something pointing here, I have now something pointing there. Okay. So, the eigenvectors of the angular momentum have a definite parity, and the eigenvectors of the Hamiltonian, because it depends only on r and it's isotropic in theta and phi, have also a definite parity. What is this parity? Let's check. Okay, the parity with M is very clear. Even it's +1, odd is -1. But what happens for the part that depends on theta? Let's write it down explicitly. So it's a Legendre polynomial of cosine of pi minus theta. So the parity of the Legendre polynomials depend on L minus M. So if we combine the Legendre polynomial dependence and what we got for phi, which was minus 1 to the power of n, so the parity depends only on L, not on M. Okay. We will have now a temporary stop on angular momentum. We haven't concluded everything that we want to know about angular momentum. We have concluded everything we need in order to solve the hydrogen atom, because now we have the solution for theta and phi. What is left about angular momentum is the question how to combine angular momentum. Why is that important? For a lot of reasons. I'll just mention here two. One, you know that the spin of a neutron or a proton is half. But you know also, or maybe you have read somewhere, don't know, but you have read somewhere that a proton and a neutron are composed of 3 quarks. Each one of them will spin half. How do you combine the spins of each of these 3 quarks and get which each is half and get half? So in order to understand these types of questions, which appear in particle physics all the time, you need to know how to combine angular momentum. Another reason it has to do with the more modern applications of quantum computing. What, at the end of the day, what is a computer? Computer is some device that manipulates zeros and ones. Okay, so you have a list of zeros and one, and you have some rules how to manipulate them and come out with some output. You have an input of zeros and ones, you do something, you come out with output. What is a quantum computer? You have a series of particles which have zeros and one, but how physically you implement a 0 and 1? Spin half and minus half. So you have a series of such particles, so your state will be actually a series of halves and minus halves. How do you write down the Hilbert space of such a series? Which is equivalent to asking how you write down the Hilbert space represented a neutron, a proton. There you're limited to 3. Here you're limited to the number of qubits you have in your computer. But how do you write it down? How do you combine these states in order to give the overall state of the quantum computer? And how do you manipulate these states in order to get some output? That will come back towards the end of the course. So we finished and didn't finish the question of angular momentum. We know everything that we need to know about the angular momentum of a single particle. It's important to know about how you combine, or how do you write the angular momentum of more than one particle. Okay, so back to hydrogen atoms. So we know everything on the part that depends on theta and phi. All that remains, all with parentheses, is to solve the R part. You remember that we wrote down an equation and left it hanging there. So let's first solve theta and phi. We solved, great. Now we're going back to it. So you remember that we defined a function u that is depends on large R, which was the radial part that depends on R of our wave function, and it's actually very similar to a regular one-dimensional Schrödinger potential, except for two things. One is that R must be larger than 0. And the second, that we have here an effective term. Which is the original radial potential and at the end of the day, once we solve it, we'll have to take u and divide it by R, because that was the substitution that we performed in order to get to this equation. Okay. Now, we'll do here a series of guesses in order to solve this differential equation. What do I mean by guesses? We have enough information to know something about the behavior of the wave function in infinity and at 0. And we'll use it in order to get some idea what is this function. Okay, we know that we'll have normalization on an integration between 0 and infinity. So it's clear that u must go to 0 when R goes to infinity. That's the mathematical conclusion. The physical, it's completely clear. We have here a bound state. A bound state must go to 0 at infinity. Okay, the second thing that we know let's look what happens at 0. Otherwise, I'll get here a divergence at 0 of the integral. Again, can't be because of normalization. Okay. Now we have also this guy taking part in the solution. But at R, let's look for a moment on the limit of R going to 0. If VR diverges slower than 1 over R squared, this term is much more important, closer to 0 than this part. So, for L not equal 0, why not equal 0? Because if it's equal 0, this term is killed in any case, and the only important term is VR. We can approximate the behavior at R going to 0 Okay, what did I do here? I threw out this part. And I'm assuming that I'm looking on the low energy part. So I'm throwing out the E. Okay, this is an easy equation. It has either right? Because if you perform a derivative twice on this, it will pull out L plus 1 and L. In both cases, it's a solution. But this can't be a solution. because L has to be here at least 1. It's not 0, and L comes as an integer. And this doesn't correspond to this limit. So I know that any solution that I'll guess here for the wave function has to fulfill that it goes around 0 like r to the power L plus 1. Let's look on the other limit. For the other limit, v of r at infinity goes to 0. Why do I choose this limit? Because I want to have something similar to the hydrogen atom, or to where v is 1 over r, which goes down to at infinity to 0. Okay. Should we worry about the L dependence there?
No, because it's too large.
No, because it's 0. Because it's L times L plus 1 divided by r squared. At infinity, r squared kills everything, so I don't care about it. So I'm left only with 2 terms. Now, we'll be interested in the hydrogen atom for the bounded states. Meaning, E smaller than 0. Just look on the potential, must be smaller than 0. So the solution is the minus here is because E is smaller than 0. Just to emphasize that we are taking the positive part of the square root. Okay, so it must fall off exponentially. If we are looking on the unbounded case, So we have something that looks like the free particle, so one-dimensional solutions. Not surprising, because we are at a point where the potential is essentially zero. So the particle should behave like a free particle in the case where we're unbounded. But there's one small difference. Here we wrote down U. In real space, we don't have U, we have R. If you want to understand this solution physically, think about a particle that was in the origin at zero, time zero. Then it starts spreading out. When it spreads out, its amplitude has to go down like 1 over r, because the probability goes down like, has to be constant, and therefore the square of the wave function has to go down as 1 over r squared, in order that the integration on theta and phi will give us a constant. So that's exactly the solution for incoming and outgoing waves in spherical harmonics, which you have met as Bessel's and depending on the boundary condition, what form exactly of the Bessel function you have. Why are these important? These are important for scattering problems. If I scatter an incoming particle on some other particle or an obstacle and it radiates out, this is exactly the form of the solution. If you want to visualize it, it's like a wave hitting a rock and creating concentric spheres around this rock. So, what remains to be done? Well, sew up all these solutions. We have it at zero. It has to behave like r to the power l plus 1. We have it at infinity. It must behave like a decaying exponential. How does it behave in the middle? These details depend on the particular form of V. And what we'll do in the next lecture is solve it for the hydrogen atom, for a particular 1 over the Coulomb potential 1 over r. Everything that I did till now for weak potentials, meaning potentials that don't behave strong as 1 over r squared, is correct for any form. Okay, so see you next week. Thank you.